Good morning, everyone. My name is Junke and I'm from University College London, Mechanical Engineering Department. The topic of my presentation is about the abstract fluid structure interaction analysis of a valvuloplasty balloon catheter inside the aorta. So, first of all, I will introduce the clinical statement for the topic, the challenge of the cardiovascular intervention for aortic stenosis, which is one of the most common heart valve diseases and results in the narrow of the valve opening, as you can see in the picture on the left. The normal valve can be opened fully, while the diseased valve is attached with calcification, which leaves the leaflet stiff and thicker to avoid it open fully. There is an interventional treatment called balloon aortic valvuloplasty. It is a simple low-cost intervention treatment using a balloon catheter to insert inside the aortic valve, open the valve, and break the calcification. It can also be regarded as the bridge to valve replacement for pre-dilatation. However, during the procedure, the balloon is inflated fully to obstruct the blood outflow tract, which can push the balloon outwards and cause the tissue damage. So a technique called rapid ventricular pacing is required to increase the heartbeat to reduce blood pressure and cardiac output to keep the balloon stable. As shown in the video, when the balloon is inflated, the heartbeat increases to keep it stable. However, RVP is still affected by some major severe potential complications and intraoperative technical requirements. And new non-occlusive balloon catheter designed recently, as shown in the right figures. It has an aortic, allowing balloon outflow to keep the balloon stable. However, it lacks enough understanding of clinical outcomes. Therefore, an understanding of the balloon catheter mechanisms to find an approach to reduce the use of RVP and keep the balloon stable itself is needed. On the other hand, finite element method has been widely used for medical procedure simulation to optimize the design of medical devices such as stent valve prosthesis. The left figure shows a balloon inserted inside a stenosis artery for investigating the interaction during the balloon inflection. However, the fluid environment including the interaction is needed. Therefore, both dilatation and stability achieved by the inflation and deflation procedures of a commercially available device are worth to be investigated using computational model. So there are two contributions in this abstract. A three-folded deflected balloon was created to obtain the balloon models with different volume inside. Here is the balloon deflected to the three-folded configuration. Another one is solving fluid structure interaction problem to know the balloon vertical displacement changing along the aorta, where the FSI model is coupling via immersed boundary Wurdemann approach. The three-folded deflected balloon model was created by an unstretched inflated balloon under the camera measurement and reconstructed via computer-aided design software. And then a suction or inner negative pressure was applied to the balloon membrane to form a star-shaped balloon, which followed by an iris mechanism to creep as three-folded configurations, which means to have rigid planes radial inwards movement to creep it. To get balloon model with different volume, quantitative simulation was used to inflate a three-folded balloon with two extremities fixed. As shown in the video, you can inflate the balloon to any volume. Then different models were obtained. When it came to FSI simulation, the balloon with bended catheter model was inserted inside an aorta with an arch. The catheter was touching to the upper inner wall of the aorta. The simulation time is about 0.2 seconds, which is an average time of the systolic duration. The aorta is simplified as a rigid fixed body. The inlet boundary was applied as the parabolic profile velocity as shown in the video, and the velocity changed with the time is shown in the plot. For the outlet section, zero pressure was applied. Here is the result for the simulation. The inflation result of the three-folded balloon model was shown as pressure volume curve, which can be divided into three regions. The green one is before the balloon membrane stretched. The yellow one is the part of the membrane start to stretch. And the orange one is the membrane stretching totally until it's reaching the maximal diameter. So this curve from the simulation shows a similar trend with the curve from experiment data in the previous study, which can indirectly validate our balloon model. For the FSI simulation result, the video shows the parabolic flow rate above the inlet section, and the balloon catheter was moving by the flow. The left plot shows the maximal displacement of the balloon, where a monotonically linear increase of the displacement along the volume, and from 8 to 10 millimeter of the displacement have a step. In this abstract, the model is the first attempt to apply two-way strong coupling between the balloon catheter with a fluid environment. A step is shown for displacement changing with the inner volume, which indicated that there is a value of the balloon volume can be deflected during the systolic time to keep the balloon relatively stable, which means we can achieve the balloon stability by deflating the balloon to one volume to keep it stable. For the future works, the velocity and pressure combination boundary conditions can be applied to more reality blood flow. The leaflets with the sinews inside the aortic root can be involved to have different pressure on the two sides of the balloon, which means the displacement with the balloon will be more reality and achieved. It can be validated by the experiment test in the future. So this is all my presentation. Thanks for your listening.